This is my sixth lecture on matrices. I am Ms. RANJANA DUTTA from the Department of Mathematics, the Graduate School College for Women. Today we will study the inverse, adjoint, etc. of a square matrix. Mind it should be a square matrix. Square matrix means the number of rows should be equal to the number of columns. Then we call the matrix as a square matrix. Let A is equal to Aij n cross n matrix, and the transpose B dash of the matrix the transpose B dash of the matrix is B is equal to A Ji n cross n matrix. Then Aj denotes the cofactor of the element Aij in the determinant A, is called the adjoint of the matrix A and is denoted by the symbol adjoint A. Again, we will explain it broadly. See, A is equal to A11, A12, A1n, and next one is A21, A22, and 2n. Similarly, AN1, AN2, ANn is a square matrix. Now, adjoint A is equal to the transpose of the matrix, matrix of cofactors. So, see, you are to find the cofactor of A11, small a11, and that is capital A11, and then the cofactor of small a12 is equal to capital A12. Similarly, the cofactor of A21, A22, capital A22, and so on. And the adjoint A is equal to the transpose of this matrix. That is, A1 row should be converted into columns should be converted into rows. That is equal to A11, A21, and A1n1. That is first row. First column is converted into first row. Similarly, the second and third, and so on. Now, this is the form to how to find the adjoint of A. So we will discuss some theorem on it, but before going to that theorem, I want to explain one example of this theorem. Find the adjoint of the matrix A 1, 1, 1, 1, 2, minus 3, 2, minus 1, 3. And verify that A into adjoint A is equal to adjoint A into A is equal to determinant of A into In, means the unit matrix. Now, you have given the matrix A. Now, at first, find the determinant of this matrix. So, you know how to find the determinant. It is very easy. Also shown it here. So, after calculating, we find the determinant of A is equal to minus 11. Now, how to find the cofactor of small a11, and the cofactor of small a11 is known as capital A11. So, for finding the cofactor of the first value, that is 1, that is small a11, we leave the first row and the first column, and then find the determinant of 2 minus 3 minus 1 and 3. So after calculating, we get its value is 3. Now to find the cofactor of the second element of the first row, that is A11, we should leave the first row and the second column because this is in the second column. So we write 1 minus 3, 2 and 3, and after calculating we get its value is minus 9. So similarly, you can see how the cofactors are calculated. You do it on your own, and then we find that the matrix of the cofactors, that is B is equal to the first cofactor is 3 and A12 is minus 9, then A13 is minus 5, and so on. Now, adjoint A can be found out by taking the transpose of these cofactors. That is the matrix obtained by transposing B. That is B dash is equal to 3 minus 9, 5 in the first column, and then 4 minus 4, 1, 3 in the second column, and such a way. And I have written what they say. That is A11 becomes A11, A12, A13, and so on. So if we multiply A into adjoint A, so A means the original matrix given, and adjoint A you calculated. Now to multiply this, after calculation you can see it gives the value minus 11, 0, 0, 0 minus 11, 0, 0, 0 minus 11, and we see that minus 11 is the value of the determinant A. So we can write it as A into IN. IN means the unit matrix. So A is equal to minus 11. So this way we can also see that adjoint A taking first and then taking A, that is after that A, we also give the same result. So we can say that this A into adjoint A is equal to adjoint A into A is equal to modulus of A into IN. So now we will discuss about the theorem given by adjoint A into A is equal to A into adjoint A is equal to determinant A into IN. See here, when we multiply A into adjoint A, now A is written small a11, small a12, small a13, and small 21, 22, 23, and the adjoint A can be written as I write it here, A11, A21, A31, A12, A22, A32, and so on. You can see. When we multiply the first row by, multiply this to A into adjoint A. See here, we multiply small a11 into capital A11, then small plus small a12 into capital A12, and small a13 into capital A13. Multiplying and then adding, we get the first value C. Here, small a11, capital A11, small a12 into capital A12, small a13 into capital A13. This, when multiplied, we will give the determinant, the value of the determinant A. But in the second case, if I multiply by the first row by the second column of adjoint A, we find that a small a11 is multiplied with capital A21. Small a12 is multiplied with capital A22. Small a13 is multiplied by capital 123, which gives the value 0. Again, I am saying this gives the value 0. Here, small aik is equal to capital AJK, where I is equal to J. Here I is 1 and here I is 1. K is 1 and K is 1. So again I am saying for the second row and second column, that is value of A22 when multiplied, it also gives the determinant A. That is second row and second column. Small a21 into capital A21. Small a22 into capital A22. Small a23 into capital A23, which is the value of the second element of the second row and second column, which when multiplied gives us the value of the determinant. Similarly, the last value of the matrix when multiplied also gives the determinant A, which can you see from the example given. Now we will discuss the theorem given. If A be any n-rowed square matrix, then show that adjoint A into A is equal to A into adjoint A is equal to determinant of A into In. The theorem states that the matrices A and adjoint A are commutative. Commutative means when AB is equal to BA, then we say that A and B are commutative. They are commutative. That their product is a scalar matrix, every diagonal element of which is determinant of A. Let A is equal to Aij n cross n square matrix. Then A adjoint A is equal to Bij n cross n Bji n cross A matrix. Then Bij is equal to Aji, the cofactor of Ji in A. Similarly, when we multiplied A into adjoint A, then the ij element of A adjoint A is equal to the summation of, as I told you and explained earlier, that is equal to Ajk into capital Aik into capital Ajk. K because the second values are same for when we multiply the both. So this is equal to 0 when A or 0 or determinant of A according as I is not equal to J and is equal to determinant A when I is equal to J. Therefore, the ijth element of A into adjoint A is equal to determinant of A if I is equal to J and is equal to 0 if I is not equal to J. In other words, all the elements of A adjoint A along the principal diagonal are equal to determinant of A, and the non-diagonal elements are equal to 0. So this is the theorem. Mind it, this is very important theorem, and it is often comes in the exam. So today this much only. Thank you.